As we said before, using hydrogen to decarbonize or electrify is indirect because you are using energy to produce hydrogen, let's say green hydrogen, by using renewable energies, and there are places where hydrogen can be used to carbonize as opposed to using directly renewable energy. Keeping that in mind, you need power to hydrogen, so you need to worry about the same things as before: technology and infrastructure, market design and regulation, system planning and operation, and business models. Let's start here. Pressurized electrolyzers. That's alkalinity. Alkaline electrolyzers. Electrolyzer is basically where you're splitting some chemical like water to produce hydrogen. PEM electrolyzer, that's polymer electrolyte membrane. These are technologies, you can imagine there is a membrane, you are pushing water through and you are separating out hydrogen from something else. SOEC is solid oxide electrolyzer cell. AEM is anion exchange membrane. These are technologies that I will learn about, but right now I have read about them and teaching for the first time, so don't remember all of the acronyms offhand. Compressed hydrogen storage. Hydrogen, it always comes up as whether it's dangerous, whether it'll explode, how to transport it, whether it's just a pipeline or whether you can compress it enough, because how much, it's very light, so energy density in some sense is very low compared to oil or gas, so you need to worry about carrying a lot of it in some form, so compressed storage is a big thing. Liquefied hydrogen is of course another thing. Everything has energy associated with them, so you're always having to go and make sure that in a circular sense, end-to-end life cycle analysis sense, whether you're producing hydrogen and compressing it or liquefying it, you're still coming out positive in terms of energy yields, right? So hydrogen ready equipment, so that's not easy because Toyota invested a lot in fuel cells and bet big on going hydrogen, but didn't work out, so they are struggling. Digital backbone for green hydrogen production and hydrogen leakage detection, which is another worry that bothers a lot of people. So with EVs you have range anxiety as to whether the battery will take you long enough or whether you'll have a charging station along the way. Now the range of battery vehicles on one charge is getting longer and longer, 200, 300, 400 kilometers, which makes people comfortable once they get used to it. With hydrogen you have the leakage problem that people get freaked out about. In terms of market design and regulation, you have additionality principle. So basically additionality means you are doing something that is beyond what would happen anyways. Okay, so you have to figure out what this is in the hydrogen, power to hydrogen. Renewable PPA for green hydrogen. Again, sorry about that. Power purchase agreement. These are when utility companies rely on aggregating and selling or buying and selling, so power purchase agreements. Could be a town, community doing that as well. Cost effective electricity tariffs, electrolyzers as grid service providers. So can you directly go from electrolyzer technologies here feeding into a grid, power grid? So that's kind of good way to think about it. Certificates about various requirements on safety, cleanliness, supply, reliability, whatever it is in terms of design and regulations. Hydrogen purchase agreement as opposed to power. Carbon contracts for difference. So what is being saved additionally in terms of is it going to be part of the offset? Is it going to be priced in some ways, and so on? I'm being a little brief on that. You need to read up. Regulatory framework for hydrogen networks, streamlined permitting for electrolyzer projects, quality infrastructure or green infrastructure for green hydrogen, and regulatory sandboxes where you play and figure out what has to evolve in terms of cost effectiveness and profitability, I suppose. In terms of system planning and operation, you have electricity TSOs, which are transmission system operator, including hydrogen facilities in their planning. So electricity transmission system operators must consider hydrogen as part of their planning. Co-locating electrolyzers with renewable generators, so onshore and offshore. There are some ideas of offshore hydrogen production, green hydrogen production, desalination, and so on that I have discussed elsewhere. Smart hydrogen storage operation and P2P purchasing, which is power to power routes. Long-term hydrogen storage, leak proof, and maintaining the energy, pressure, liquefied, whatever is involved in terms of long-term hydrogen storage. Cooperation between electricity and gas network operators. So you have cables running electricity, but you may need pipelines for hydrogen, just like liquid natural gas and so on. In terms of business model, local hydrogen demand. Obviously, anytime you can do production and consumption locally, you save a lot on infrastructure losses, costs, etc. Hydrogen trade, you can go and figure out what that means. Hydrogen industrial hub. How can you have a utility scale hydrogen hub to serve industries? Maybe revenues from flexibility provided to the power system and sale of electrolysis byproducts like oxygen and heat. So if you're splitting water with electrolyzers to produce hydrogen, then you have oxygen and of course heat being produced in the process. Typically they involve electrolysis. Splitting water is not done at cold temperatures, include basically liquid pyrolysis. I'm using random words, but you have heat generated, so can that be captured and used as well? Okay, so following the other podcasts, we will leave this power to hydrogen by itself, and I should be able to conclude in the next podcast as far as smart electrification is concerned. So we looked at end-use sectors here, basically in terms of power for mobility and power for hydrogen and power power for heating and cooling. Okay, come back and see you in the final podcast of smart electrification.